Okay, so in this video, we will find the area of the region bounded by the curves y equals 2x and y equals x squared. Now if you notice, this is the exact same problem as in the previous video. Right, we already found the points of intersection to be 0, 0 and 2, 4 between the curves 2x and x squared. And we found in the previous video that the area of this region is exactly 4 over 3. But if you recall, we obtained 4/3 as the area of this region by covering up the region using vertical rectangles. So in this video, we want to present an alternate solution, now finding the area of the region by covering it up, not with vertical rectangles, but with horizontal rectangles. So we take a small horizontal rectangle. Now the width of the rectangle is a very small segment along the y-axis. So we, of course, denote this by dy. And again, dy is an infinitesimal change in y. So a change in y that approaches 0, because only by letting the width of our rectangles approach 0 can we then obtain the exact area of the region. Now this rectangle is positioned along the y-axis now, and as we need the measurements for a generic rectangle, as we will then move it up and down the region to cover it up, it is positioned at an arbitrary y value, so of course we denote its position simply by y. So all we're missing now is the length of our rectangle. Well, it is clearly a segment now along the x-axis, so we need the measurement in x for this rectangle. So we have here the right-hand point, we need its x value, and we have here the left-hand point, we need its x value. And again, because we have here dy as the width of our rectangle, everything we measure must be a function of y. So at the right-hand point of our interval, we are on the curve y equals x squared. So if we isolate x in terms of y, of course we take the square root of both sides, and so x is simply root of y. Thinking of integration, we will write this as y to the power of 1 over 2. So we have the x value in terms of y for the right-hand point of our rectangle. What about the left-hand point, where at the left-hand point of our rectangle we are now on the line y equals 2x. We need to solve for x in terms of y, divide by 2. So x is of course y over 2, or a half times y. And so we have the x value in terms of y for the left-hand point of the rectangle. And now we're essentially done. So the area of this rectangle will be the length of the rectangle times the width. So if I call this L for the length of the rectangle, well, again, it's the segment along the x-axis. So the length of the segment will of course be the larger x value minus the smaller x value, of course in terms of y. So the area of an infinitesimal rectangle is the length times the width of the rectangle. So we obtain y to the 1/2 minus a half y times dy, length times the width of the rectangle. We now have the area of an infinitesimal rectangle. And to obtain, of course, the entire area of the region, we have to sum the area of our infinitesimal rectangles from where to where. Well, here you have to be careful. Our rectangles are positioned along not the x-axis as before, but along the y-axis. So we will cover up the region by moving up and down our rectangles. So where do they start? They start all the way here at the first point of intersection where y is equal to 0. And they go all the way up to to the second point of intersection where y is equal to 4. So if you sum the area of all these infinitesimal rectangles from y0 to y equals 4, you will have covered up the region entirely. Therefore, this will return the exact area of the region. And now, of course, to evaluate this, we use the fundamental theorem of calculus. We find an antiderivative from the power rule. So add 1 to the exponent. So 1/2 plus 1 is 3/2. Divide by 3/2, of course, times 2/3. Minus 1/2 is a constant multiple. Power rule on y gives you y squared over 2, but 1/2 times 1/2 is 1/4. So minus 1/4 y squared from 0 to 4. Now we replace y by 4. So 4 to the 3/2. Apply first as a square root. The square root of 4 is 2. 2 cubed is 8, times 2 is 16, so we have 16 over 3. Minus 4 squared is 16 over 4 is 4. Minus the antiderivative when y is equal to 0, which of course is simply 0. Putting everything over 3, 4 is 12 over 3, and 16 minus 12 is 4 over 3, just as before. The exact area of this region is 4 over 3. And you might wonder, well, what was the point of introducing this new solution? Well, the idea is the following. Every time you look at a region in the xy plane, bounded by 2, 3, or any number of curves, and you want to find the exact area of this region, you always have two options. You can either cover up the region with a set of vertical rectangles, and then you will integrate with respect to x, or you can cover up the region with a set of horizontal rectangles, and then you will integrate with respect to y. This is useful because in some cases it will be a simpler problem using vertical rectangles. In other cases it will be a simpler problem using horizontal rectangles. So before you find the exact area of any region in the xy plane, always ask yourself if you are better off with vertical rectangles or horizontal rectangles. Now in this example, both vertical and horizontal rectangles led to a fairly equivalent solution, but in some cases, one choice will lead to a much more elegant and simpler solution. So always keep this in mind. And that's it.